Good morning. Morning, guys. How you doing so far? Morning. Are you guys doing okay? No? Why? What's up? Chemotherapeutics is tough for you? Antibiotics? Okay. Let's see if you can change your mind by the end of today's lecture, okay? I'm sure you will. Well, we can make a deal. If something is not clear, we could just remove it out of the final, okay? Make sense? Yeah? Nothing is clear? Just wait. Give me the chance. So we'll actually go one concept or one, topic by another until we reach to the last and the end. And if something is not clear, then we'll take it out of the final exam. All right, you have a speech. All right, what's up?
Dr. Khashan, we just wanted to say thank you so much for everything you've done for us this semester.
Sure.
We heard. Why would I expect anything different? We heard a rumor that you're leaving us.
A rumor? It's a truth. It's not.
Okay. So you're leaving. So we just wanted to show our appreciation. So we have a few things for you.
Oh, great! Thank you so much. Oh, thank you, guys. Thank you so much. Thank you. Thank you so much. All right.
We have a couple things for you. Lauren,
You'll make me cry now.
Lauren here made the Snippy Dippy card for you, and everybody signed it. So.
Oh my God. Awesome.
Going through this.
Thank you so much. Of course, yes, I will. Thank you. I really appreciate it, guys. Thank you so much.
And on behalf of the class, we got you a little gift.
Oh my God.
And the last thing we got for you, this really nice little plaque. It just says thank you for all the hard work you've done, and we appreciate it.
Oh my God. Thank you so much. Well, now I'm gonna change my mind. I'm not gonna quit.
Darn,
let's do this again.
So there you go.
Thank you so much. I appreciate it.
Yeah.
Thank you, guys. Thank you so much. Thanks a lot. Okay, so we're talking about antibiotics. So we're gonna move from one topic to another, and then if something is not clear, we could just skip it, take it off the final. Okay, so it's gonna be your decision. Okay, so if we talk about an exercise and you master the whole thing in the exercise, then great. If you don't, then we'll just take it off the final. Deal? But be nice now. Don't take off everything. Okay, so how many people are not at the start screen? Raise your hand up high. Of course, the people who are standing here. All right, so let's give you a few more minutes. Thank you, Kendra. Thank you, everyone. No, thank you. Melodies. I'll be working for Walmart actually. Walmart.
Oh, Walmart. So we're gonna come ask our questions there.
Sure, you should. Yeah. Yeah. Yes. I might. So far, I'm not. But yeah, sure. Yeah. Yeah, then I can harass you in the in the pharmacy about medchem concepts. You know. Yes, I'll be here. Yeah. So far I'm floating actually. So I'll be everywhere.
Sweet, we get to stop you.
That's right.
We'll figure out your work.
Sure. I'm sorry. So it's basically East Texas, Longview, Marshall, and all this area. No, no, I'm here. Yeah. Yes. Yeah. Yeah. I'll be here. Oh no, no, no. It's yeah. Sure. Yeah. You should stop by and ask questions. Okay. Yes. Yeah. What? um. No, because it's complicated. Nope. Too late. Okay. If you are not at the start screen, can you raise your hand? If you are not at the start screen, oh, everybody is, except one person. Can you raise your hand up high if you're not, so I can see? Two more people? Oh, three, four, five. Okay. Huh? I'm sorry? Yeah, I think it's okay. Okay, let's try again. See how many is not in the start screen. Okay, if you're not again, can you raise your hand up high so I can see? Can you please raise your hand? We're gonna start. If you're not ready. Okay. Okay, so should be only 5 questions and 8 minutes. Go ahead and start. Okay. Good luck. Okay, you could start working as a team now. Okay, so let's go through the questions. The first one, what is the target for clavulanic acid? We all know it's beta-lactamase. So which enzyme does penicillin target then? Transcriptase. So what does clavulanic acid do then? Well, let me ask you a different question. What does the beta-lactamase enzyme do? It breaks down beta-lactam, which is essential for the activity of these beta-lactams drugs, right? Penicillin, cephalosporin. So clavulanic acid is designed to actually protect or distract the beta-lactamase enzyme, okay? So clavulanic acid will bind to the beta-lactamase enzyme, and then penicillin can work freely, hopefully, okay? Any questions about this? No? Yes. Okay, so we have two enzymes. The transpeptidase is what penicillin attacks, okay? So it's important for building the cell wall. Now, resistant bacteria, they produce beta-lactamase, which is actually another isozyme of the transpeptidase. But anyway, they have beta-lactamase, which is able to bind to the penicillins and all these beta-lactams, and then basically break them. That's how bacteria become resistant, okay? So to get rid of, or to fix this problem with bacteria who are resistant, we administer clavulanic acid. I'm sure you all have seen Augmentin, which has amoxicillin and clavulanic acid. So the clavulanic acid will actually bind to the beta-lactamase, okay? And this way will allow the penicillin to do its job, okay? Now, not only that, clavulanic acid actually binds irreversibly to the beta-lactamase. Why is this important? Because it actually binds to the enzyme, it stays there forever, it inhibits it forever, okay? But if it binds reversibly, then the enzyme is gonna still be able to break down the penicillin or the beta-lactamase, okay? We will visit this again in one of the application exercises, okay? Okay, question number 2. Which structural feature is more effective than making methicillin more effective than penicillin G? So we're comparing two things, penicillin G and methicillin. There is a structural feature in methicillin that makes it resistant. Which one is that? Is it the aromatic ring in red, or the carboxylic acid, the beta-lactam ring, or the methoxy groups? We all know it's methoxy groups. What do they do? Steric hindrance, they make a shield, a bulky shield to protect the beta-lactam. They protect beta-lactam from what? Beta-lactamase, okay? But it's the same part of the molecule that's also important to bind to, to inhibit the peptidase, isn't it? So how do we protect this from beta-lactamase, but not from peptidases? I'm sorry, the transpeptidases. Did you hear that, guys? So this bulky group should have, I guess, the right size. If it's too small, it's not going to protect the beta-lactam. If it's too large, it's going to protect the beta-lactam from both the beta-lactamase and the transpeptidase, which means the drug will not be effective. So it's only a methyl or ethyl group, one carbon, two group, or two carbons that are able to do that. So they protect the group from the beta-lactamase enzyme, but at the same time, the antibiotic is still be able to attack the transpeptidase enzyme. Make sense? You got this, everybody, 100%? Okay. We'll visit this again when we talk about the resistance of the antibiotics, okay? Right. Question number 3, which structural feature is most crucial for the mechanism of penicillin? We all know it's A. Everybody agrees? What? You cannot see the color. You mean in the computer? You cannot see the color? Really? Okay. So which color did you see? Huh? The yellow was not clear. Say it again. Which one? Green is nice. Okay. You guys are so picky. We could not see the color. Any questions about this? Any questions about this, guys? All right. Next one. Yes, sir. Okay, sure. In the final, I'll make it clearer. Right. Number 4. What is true about erythromycin? Let's go through one by one. It is stable to the low pH acidic environment of stomach. We all agree it is not stable to the acidic condition. Okay. Erythromycin tablets must be in extended release form. Which form it should be in? Delayed release. Okay. We all got that? Because it's not stable to the acid of the stomach. So one way to solve the problem, there are other ways we'll talk about today, but one way is to make it in an enteric coated format such that it passes the stomach to the intestine, okay? Right. Number 3, the prodrug erythromycin ethyl succinate is used in oral suspension to mask the bitter taste of the drug. We all agree this is right? Okay, so one of the techniques of a prodrug, or one of the uses of prodrug, is actually mask the taste of the drug. You could either make it insoluble, such that when you take it orally, it does not dissolve, it does not bind to the taste buds, okay? Or if you know which chemical feature is responsible for giving this bad taste, and if it's not one of the pharmacophoric groups, you could actually modify it or mask it, do something such that it does not give this bad taste. Make sense?
I think you've asked a question like this before, and I assumed I knew the answer, and I guess I was wrong. So one of the reasons to make a prodrug is just for taste?
Yeah. Yes. Yeah. It's one of the yeah.
They have the normal version of the drug, and then they actually design and successfully.
Yes, only to mask the taste. Yes, especially if it's a suspension, then when you take it or by mouth, then especially for kids, then it could actually give the bad taste. So they formulate it in a way.
Marketing-wise, do you want the bad tasting, or do you want the $100-something good taste?
Well, I mean, you certainly need the good taste, but then the price, is negotiable. So, I mean, I'm not negotiable. I'm sorry. It might vary. Sometimes making a minor change can make the drug really expensive. It might need like a lot of chemical processes, so it could be expensive. Sometimes not. So that's another factor. So yes, you have two different factors. Okay. But of course, you have the other option of you could flavor the suspension. So that's another way to solve the problem.
Since I assume that was wrong,
Mhm.
whatever other question, I wonder what else I said was right. I'm just saying that for me to not get this number of question about it, I must have gotten something else.
Okay. Okay. Part D, it can be used to treat ulcers caused by Helicobacter pylori. Why? Why? Where is the bacteria located? In the stomach. So if the stomach is acidic and this drug cannot be stable to the acid, so it cannot be, it cannot be used. I know this was a tough one only by looking at your, team responses when the whole team is not able to find the answer. So, so we'll make this one, okay? The same with number 5. All right. Number 5. Number 5. All right. You really love points, don't you? Okay. So I mean, only looking at your answers as a team, that's the reason I want to do that. Okay, so but let's learn about number 5. All right. Number 5. What statement is most true? Or what statement is true? Cefazolin, which is this drug here, can cause disulfiram-like reaction if taken with alcohol. So this actually might need some explanation. Have you guys heard of disulfiram reaction? Probably no. Okay. Okay. Have you heard of a drug called antabuse? No. Okay. There's a drug called antabuse, which is simply the generic name for it is disulfiram. So people who abuse alcohol, they're addicted to alcohol, they take this drug to help them with their addiction. What this drug does is basically prevent the metabolism of the alcohol. So when you take even a small amount of alcohol, guess what? It's like drinking a lot of alcohol, right? So you get hangover, you get all these horrible, symptoms. Okay, so that's how they prevent them or punish them, I guess, for taking even just a little amount of alcohol. So the drug itself is called, the generic name or the chemical name is called disulfiram. Okay, some drugs, like our friend here, are also able to inhibit the metabolism of alcohol. There are some other drugs besides this example that can also inhibit the metabolism of alcohol. So anytime you take this drug, you get the same effect of the antabuse. We get the same effect with disulfiram. So we call this effect disulfiram-like reaction. Okay? And in fact, it's this chemical structure, this one here, is the one that is responsible for the disulfiram-like reaction. If you see this feature in any of the other cephalosporins, then you should know that it would cause disulfiram-like reaction, but it's not the only one. There's other structures, okay? You guys know what metronidazole is? Flagyl, okay? So flagyl metronidazole is another example of a drug that can cause disulfiram-like reaction, okay? Because it inhibits the metabolism of alcohol. You got it, everyone? Use what? Use like the antibiotic? I mean, in theory you could, but why would you wanna give antibiotic if you have the disulfiram itself, right? I mean, in theory you could use any of these antibiotics that have the disulfiram-like reaction, and it's not just antibiotics, there's also antifungal and other drugs in market that cause this effect. But of course, if your goal is to treat alcohol abuse, then I would use the disulfiram, okay? Now, Of course, you do not want to use antibiotic for no reason because you might develop resistant bacteria. Okay. Yes.
Have you ever held any therapy like with somebody combining that software and maybe Tylenol and alcohol, so such that the person does not get the effect of Tylenol and alcohol. That one inhibits the digestion of alcohol. Does that make sense?
I never did. I know. So his question is, you know, we learned about Tylenol toxicity and how it could be enhanced by using alcohol. Okay. So he's trying to come up with something where you have Tylenol and disulfiram. I never heard any way they could use both. But if you do, then it's actually, this is gonna inhibit metabolism of alcohol. So you actually have more alcohol, which means it's gonna make it worse for the Tylenol. Okay.
Since if you have someone who's drinking enough that they shouldn't be taking Tylenol, the moment they take Tylenol, they're not going to be right. I mean, the moment they stop drinking, they're still going to be dangerous if they take Tylenol. So, but
yeah. Other questions? Any comments about this, guys? Okay, the next part, beta-lactamase inhibitors bind irreversibly to transpeptidase enzyme. So we have beta-lactamase inhibitors such as what? Clavulanic acid, okay? These are the ones that are designed to protect antibiotics. They bind irreversibly to transpeptidase. Do they bind to transpeptidase? No, where did I bind? Beta-lactamase, okay? Do they bind irreversibly? What do you think? Yes, they bind irreversibly. Yeah. Okay, so I actually accidentally underlined this one, but then I realized, no, this is what I should be underlined. So I, but it's both underlined. I didn't think about it at the minute, but now I realize it's actually irreversible for a reason, right? So, but do all beta lactams bind reversibly to the transpeptidase? Can you give me an exception? Okay, just keep that in mind because we'll visit this in the exercise, okay? We have, the beta-lactam antibiotic such as, can you name them? Penicillins, cephalosporins, carbapenems, and monobactams. Of course, other examples that we did not cover is vancomycin. But think about these four classes. Which one binds irreversibly? There is one of them that binds irreversibly, which is why the reason this one normally does not need to be combined with the beta-lactamase inhibitor. We will talk about this in one of the exercises, okay? Okay, cephalosporins are more potent than penicillins. Why is that? Say it again. They're less potent. Why is that? Why are cephalosporins less potent? Say it again.
Because the beta-lactam ring in cephalosporin
is not strained as much. Guys, we will talk about one of the exercises on the importance of the strain of this ring here. Now, as you can imagine, if this 4-member ring is attached to a 5, then it will be more strained, which means the molecule is so uncomfortable, okay? If it's attached to a 6-member ring, then the molecule is more comfortable. It is still relatively uncomfortable, but compared to penicillin, you get the point? So the strain on that ring will play a role in the potency. So the more unstrained, I guess the more strained the molecule, then it's stronger, it's more potent, okay? So we know the answer is A, correct? Okay, any questions about this? No? Okay. I think it's too early to have a break. Do you want to have a break, or should we like start with the first exercise at the end and have a break? Okay. Okay. Right. So the first exercise we'll have is actually a very interesting concept that is not covered in the material, but I really want you to think about this exercise, discuss it as a team. We all know that being exposed to antibiotics help making bacteria resistant, right? Right? Why is that? I heard somebody saying natural selection, which is very correct. That's true, but I need a simpler explanation. Why? What does that mean when you say natural selection? Say it again. Survival. What? Survival deficit. What does that mean?
Another term for natural selection.
Another term? You guys come up with two complicated terms. No. John?
Bacteria it's less efficient to have to grow extra DNA for this plasmid every time it replicates. So if you put a pressure on it of a antibiotic, then the bacteria that occasionally do have this plasmid are now more competitive than the ones that aren't growing it. They also were able to exchange DNA by various processes.
Okay, so exchanging DNA is one of the way of transferring the resistance of bacteria from one to another. I'm talking about how do the bacteria induce having how do antibiotics induce having resistant bacteria? Let me try try to explain the question in a better way. Right, so let's see. Let's see that this is somebody here, okay, and this is another person here on red. Can you see the green color? All right, it's not yellow, okay? Okay, so this person here takes too much antibiotics, okay? I'm sorry?
Reservoirs for people who are no longer sick, but growing bacteria that's got plasmids for antibiotic resistance.
Okay, that's still too much complicated. Vivian? Mm-hmm. Okay, so I'm talking about before the plasmid is transferred. So what Vivian is saying is correct. So you have a plasmid, bacteria share their DNA such that the resistant version of the bacteria is transferred from one to another. But I'm talking about before the mutation develops itself, okay? So let's say that this is a bacteria, okay? So let's say that these two people are infected. I'm putting this in the wrong place. Right. Okay, this is bacteria. Okay, so let's say that those two people are infected with the same bacteria, okay? One of them in the red takes antibiotics. The one in green has not taken any antibiotic, okay? Now think in terms of bacteria. How does the bacteria that is exposed to an antibiotic now develop resistance, while the bacteria that is not exposed to the antibiotic does not develop resistance? I mean, bacteria do not think, right? I mean, they're not going to sit in the corner and say, okay, so we got penicillins, let's do the mutation for, generate bacteria that are resistant to penicillin, or, oh, we got cephalosporin, we got this much, let's do, or, they don't have this, you've seen the movie Inside Out? So they don't have these managers bacteria sitting in the brain and say, okay, let's do this, let's do that. How do they mutate? How does mutation occur? Randomly, right? They actually, they multiply and divide so fast, okay, such that one of these versions that come out is actually resistant to the bacteria. I'm sorry, to the antibiotic, okay, accidentally, okay? When something is like the bacteria, when they develop so fast, then there is a chance that mutation can occur. And this happens in both cases, okay? But with someone who's exposed to the antibiotic, they are gonna, if accidentally this mutation occurs, then they become resistant. Someone who's not exposed, they will not. So take a minute or 2 minutes, think about it, and then we'll talk, okay?
I'm trying to figure out, how do you find out if it's irreversible inhibition of transpeptidase or not? You said if it requires a beta lactam, it's not, or if it does.
To the enzyme Okay, were you guys able to find the answer? Anybody wanna give us an idea what's going on? Well, is the question clear? Guys, is it clear what I'm trying to do here? Imagine if antibiotics are not prescription, like some other places, some of the antibiotics are actually not, can be given without a prescription. You can go to the pharmacy and ask for antibiotic, and you just take it easily without a prescription. In these regions, guess what? In these regions of the world, bacteria are more resistant, right? Because they're more exposed to the antibiotic, so they become resistant. But how do bacteria know to become resistant to one antibiotic or the other if they divide randomly? If the mutation itself occurs randomly, it's going to occur randomly. So I mean, whether it's here, whether they are exposed to antibiotic or not. Okay. So back to the question: how do the bacteria develop mutation? Only when they're exposed to certain antibiotics. So if I'm exposed to antibiotic X, then I become resistant. The mutation develops for this X antibiotic. How does this happen? How do they know? Yes.
So you'll have like a group of bacteria, and maybe one or two of them develop randomly the immunity for an antibiotic. And without an antibiotic present, they just kind of reproduce and live just like any of the other bacteria. So their genetic code doesn't really get passed on along any more than the other bacteria. But if you introduce antibiotic, all of a sudden all the other bacteria are wiped out, and you just have these few that have the immunity. So now they have no competition as far as spreading their genetic code. So that multiplies a lot more.
Excellent. Everybody got that? Everybody got that, guys? Let's reiterate this again. Can someone repeat what was just said? There we go.
What's up, guys? Okay, so what Wesley said is you have a bunch of bacteria, right? Only a few of them are resistant against an antibiotic, but it's competition, so they don't get to pass on their genes that well. So once the antibiotic comes and kills the rest that aren't resistant, those ones that are resistant have no more competition, and they can breed and spread their genes, and everyone's resistant.
Excellent. Thank you so much. Makes sense, guys? Right? Thank God I did not have to explain it. Can you raise your hand if you got this 100%? Okay, excellent. So indeed, when you introduce a certain antibiotic X, then it's going to kill everything. It's going to kill all the bacteria except the one that were randomly and accidentally created, which are resistant to the X. Now those resistant strains have nobody else to compete with, right? They're just living freely. They have all the resources, and they develop, grow, and that's what happens, okay? If you never introduce this antibiotic, then those little mutations that were resistant to X, they just, even if they appeared, they don't have chance to survive, okay? They're competing with our bacteria. Make sense now? Okay, so the next exercise, now you need a break probably? Okay, so I'll be generous with you today, 10 minutes. All right, 10 minutes break, and we'll come back at 10:05. Okay, so let's talk about exercise number 2, mechanism of action of beta-lactam antibiotics. So I know that you did not have, microbiology background, some of you, and the structure of bacteria. Have you learned about bacterial structure? Was microbiology prerequisite? Oh, good, good. So let's start by actually comparing these two. Okay, so as you can see, the gram-positive bacteria has a thicker cell wall compared to the gram-negative, okay, which is like 50 to 100 layers. Here is 200 layers. It's 2 layers, so it's like 50 times more than the gram-negative. Also, the gram-negative has this hydrophobic outside layer, okay? So when we design antibiotics, we should make sure that the antibiotic is able to reach to the inside. And it does that through this hydrophilic pore-in, okay? This is just a general overview. We also see the beta-lactamase enzymes trapped here, okay? So why do we not see the beta-lactamase enzymes with the gram-positive? Do we have gram-positive resistant bacteria? We can, right? They are less common. Also, if the beta-lactamase is released, it can actually go through this porous cell wall, and it won't be as concentrated as in the case of the gram-negative, okay? So in the case of the gram-negative, the fact that we have a membrane here outside will trap these beta-lactamase enzymes. This is why it's more common to see resistant bacteria in the gram-negative, okay? Trying to think if there is other things I wanted to cover. Okay, I'm not worried much about the details of how the cell wall is synthesized, but it's at some point, so there are too many enzymes. There are too many enzymes involved in the synthesis of the cell wall, okay? And it's the last step during the synthesis of the cell wall, which is when these chains are linked together using an enzyme called transpeptidase. This is the enzyme that the penicillins and beta-lactams inhibit. Okay, guys? So all of these antibiotics, cell wall inhibitors, they inhibit the transpeptidase enzyme, okay? Now, the next question is, do these beta-lactams drugs bind to the transpeptidase reversibly or irreversibly? It's irreversible, right? Why is that an advantage? Exactly. So imagine if these antibiotics bind reversibly to the transpeptidase. What happened? They're not going to be as efficient, right? So they can bind to the enzyme, but then if they don't bind irreversibly, if they don't form covalent bond, they can leave the enzyme can continue to do its job and building the cell wall. So having an irreversible binding is advantageous in this case, okay? If you remember, in all the other classes of drugs we have learned, when we were talking about working with drugs that act on human, our preference was for what? The reverse binding, reversible binding, or irreversible? We're looking for reversible binding, right? Because it was safer, and then we could stop the drug anytime, and then the body function would resume. with the case of the bacteria, virus, fungus, we want to have irreversible binding such that we could actually stop the function of that bacteria forever. Okay? So all these beta-lactams antibiotics, they bind irreversibly to the transpeptidase enzyme. Okay? This reaction here, I'm not too much concerned about it. I just want you to notice that at the end, you have an irreversible binding of the antibiotic with the enzyme such that no more peptide chains can be put together. And this will inhibit the cell wall synthesis. Right, so we're working on exercise number 2, and I'm trying to explain the mechanism of action of all these beta-lactams, okay? Any questions so far about the mechanism of action? Any questions? Okay, so back to exercise number 1. I assume everybody got this 100%, right? So it will be part of the final, okay? Good. Exercise number 1. As soon as you mention an exam, final or CAT, everybody is alert. Like, oh, which one? What did he say? So exercise number 1, everybody got that 100%. So it's safe to ask a question about it, right? I'm talking about number 1. So now we're talking about exercise number 2. So is everything clear about mechanism of action of the beta-lactams? Not yet? I knew it. All right, so now you're awake. So tell me what is not clear. What is not clear about the mechanism of action of the beta-lactams? Say it again. Mechanism itself? What is it? What's in the mechanism that's not clear? Okay, so the cell wall is basically chains of glycopeptides, okay? Proteins and sugar. Imagine you have chains, okay? But these chains, if they're not linked together, they can actually, leave the bacteria. They can disappear. So the job of these antibiotics, actually, the job of the enzyme transpeptidase is to actually link these chains together, okay? Imagine if you have, chains, but then if they're not linked, they could disappear. But then the enzyme link these together, okay? So, okay? It's like it seals these chains together. The beta-lactams, they inhibit this enzyme from sealing these together, okay? So they inhibit the enzyme. Now, if they bind to the enzyme reversibly, it means they can still bind and leave and do their job and then come back and bind. This is not good. We need antibiotics that can irreversibly bind to the enzyme and prevent the enzyme, forever, okay? Now, why do we care about cell wall? Why is cell wall so important to the bacteria? Right. There's a difference in the concentration, also known as osmotic pressure, outside and inside the bacteria. So as soon as the cell wall is not there, the bacteria can lyse or burst, right? Because there is difference in the concentration between inside and outside. So the cell wall protects the bacteria from, the bacterial cell from, bursting or lysing. So where is the enzyme located here? The transpeptidase. Is it located inside the cell, here or here? Inside or here or here? The transpeptidase. It's actually located here, right? So as soon as the cell wall is synthesized, it put them together, push them, put them together and push them out, okay? So when the enzyme is inhibited, the cell wall will actually be destroyed. So if the bacteria already has a cell wall, can the antibiotic work on it? What do you think? So actually it works on the dividing cells. If the bacteria is already, there, the cell wall is there, antibiotic is not going to work, right? But guess what? Bacteria developed so fast, okay? So as soon as the bacteria divide to give up 2 more bacterias and it's ready to develop another cell wall, then that's when the antibiotic works, okay? So there is actually a correlation between how fast the bacteria develop and how efficient the antibiotic is. The fastest the bacteria, the more efficient the antibiotic, okay? You will also learn at some point that we have something called mycobacterium. They are very slow bacteria. So guess what? When you give a dose of antibiotic for the mycobacterium, you actually have to give the antibiotic for like 6 to 9 months. Yes, you know why? Because you have to wait for all the bacteria to go through all the life cycle and until it reach to the part of the life cycle where the antibiotic work. Okay? So if you have 1,000 bacteria and there are some of them in different life cycles and your antibiotic works only on this stage. So in order to kill all of these bacteria, you have to give enough time for all this 1,000 bacteria to go through the life cycle and then be affected by this bacteria, by antibiotic. So when you have a bacteria that develops fast, then good, you just give the antibiotic for, depending on the antibiotic, of course, let's say 5 to 10 days, then you could actually be sure that all the bacteria that are developing have reached the stage where your antibiotic works. Okay? Exactly. That's why tuberculosis, I mean, when you treat it, then you have to give the antibiotic for 6 to 9 months to make sure that this slow growing bacteria will reach to the stage where the antibiotic works. Okay? Have you heard of the term bactericidal and bacteriostatic? What's the difference? Cidal will kill the bacteria, right? Static will freeze the bacteria from moving forward. It's not dead, it's just frozen, okay? And then when the bacteria is frozen, then your immunity will actually attack these bacteria that are frozen and get rid of them. So guess what? If someone is immunocompromised, which option would you go with? The cidal, okay? Not the static. Make sense? Okay, so back to the mechanism. And we talked about transpeptidase, bacteria inhibit this enzyme. But then on the gram-negative, we have something called lactamase enzymes. And we mentioned that gram-positive can have beta-lactamase enzymes, but they leave because this cell wall is very porous. So they can actually leave, they're not trapped. Here with the gram-negative, they are trapped, so they can protect the bacteria from the antibiotic. So first of all, lactamase enzymes are actually the same as transpeptidase enzymes. They just mutated from transpeptidase enzymes. So they're actually one form of transpeptidase, believe it or not. So they just mutated and they are able to bind to these bacteria just like transpeptidase bind to, except there is one single difference that makes them efficient. What is it? Excellent. They bind reversibly. Why is this important? Exactly. So these lactamase enzymes, like I said, they're just like transpeptidase, except with transpeptidase, the drug binds to them irreversibly, stuck forever. These lactamase enzymes, they have mutated, enhanced, they are developed such that when the antibiotic comes, they bind to them reversibly. Okay, what happens to the penicillins or cephalosporins or all these beta-lactams when they bind to the beta-lactamase? They break open, right? So as soon as the beta-lactam ring is broken, the antibiotic is not functional. So imagine the the lactamase enzymes basically breaking open an antibiotic and let it go. Move to the next antibiotic. Break open it, let it go. Break open it, let it go. And do this for all the antibiotics, right? So it's reversibly binding to these antibiotics. That's how they protect the bacteria. They break open all these antibiotics. So that's a key point. Reversible versus irreversible. Okay? Make sense, guys? Speaking of that, there's one exception among these penicillins, cephalosporins, carbapenem, monobactams. One of them actually binds irreversibly to the beta-lactamase. Which one is that? I know for sure it's carbapenem, one of them, but is monobactam too? Okay. Can someone check the notes? Anyway, so why is this important? Carbapenems and monobactam, when they bind to the lactamase enzyme, they bind irreversibly. So the enzyme is not able to break open it and move to the next one. As soon as it binds to it, yes, it will break open it, but then it's stuck with it forever. So these carbapenems are able to be used in the bacteria that are resistant to penicillin and cephalosporin. So they can be used in cases where bacteria are resistant. So if you have bacteria with beta-lactam, resistant because of the beta-lactamase, then I can use carbapenem or I think monobactam too. Say it again. How they, so just like they bind to the transpeptidase, the only thing is when they bind to the beta-lactamase, they form irreversible bond, which means they stick to the enzyme forever. So now, yes, we have beta-lactamase, but once you give enough amount of antibiotic, then these beta-lactamases will be useless, just like with the transpeptidase. Yes, Kendra. Right, so with these cases, carbapenem and monobactam, because they bind irreversibly, so they do not leave the beta-lactam, they do not leave the lactamase enzymes alone. Yes, yes, carbapenem and monobactam are exceptions. They bind irreversibly to the lactamases, okay? Yes. No, don't say sorry. Sure. Monobactam and carbapenem. Carbapenem and monobactam, they bind irreversibly to the lactamase. Yep. Okay, so let me check, make sure you got everything correct. So first of all of these antibiotics, they bind to the transpeptidase enzyme, what, reversibly or irreversibly? Irreversibly. We all get that. Otherwise, it would be useless, right? Okay. Now, all of them binds to the lactamase enzyme reversibly or irreversibly? Reversibly, with exception, which is carbapenem and monobactam. Okay, now let's talk about the beta-lactamase inhibitors, like what? Clavulanic acid, okay? Clavulanic acid is a beta-lactamase inhibitor. How does it bind to the beta-lactamase? Does it bind reversibly or irreversibly? Irreversibly, okay? So do you think we will need a beta-lactamase inhibitor in case we are using carbapenem? No. Why is that? Because carbapenem itself is able to bind to the beta-lactamase inhibitor irreversibly. You got this, guys? 100%? Not yet? Include it in the final? Not yet? Well, then ask questions. Yes, sure. And monobactam, and some monobactams actually. So to which enzyme? To lactamase enzyme irreversibly. Yes, irreversibly. Yes. Say it again. Oh, it's the same thing, guys. Anytime I say lactamase, I omit, I skip beta lactamase. It's the same. So when I say lactamase or beta lactamase, it's the same. Okay. Okay. Questions? Yes, Daniel. Which one? Oh, so. Mm-hmm. Okay, so let's focus on the beta-lactamase enzyme by itself. Okay, what's the job of this enzyme? Break open the antibiotics, right? So their job is to reversibly break, these antibiotics. So they bind to them, break them, move to the next one, right? Makes sense, because if they are stuck with one of them, they cannot function. Okay, so beta-lactamases, they protect the bacteria. So they break open all the bacteria. All the antibiotics, except carbapenem and some monobactams. Okay? Everybody got that? So the only exception is carbapenem, monobactams. They bind to the lactamase enzyme irreversibly, which means they are stuck with it forever. Does that make carbapenems better than the other antibiotics or worse? Better, right? Why? Because if the lactamase try to break open it, they're stuck with it, and the lactamase itself now is inhibited. So now these carbapenems and some monobactams are able to inhibit the lactamase as well as transpeptidase. Okay? And then we also talked about some drugs that are designed only to inhibit the beta-lactamase, okay? Such as clavulanic acid. There are two other examples, but I keep mentioning clavulanic acid because it's commonly used. You see it in the augmentin. So clavulanic acid, the only goal of this drug is to bind to the beta-lactamase irreversibly, okay, such that this enzyme is no longer able to break open the other antibiotics. That's why it's combined with amoxicillin, for example. You see in the market augmentin, amoxicillin, and clavulanic acid. Okay. Included in the final. The last part, the clavulanic acid. Okay. So if we have some antibiotic that want to reach and bind to the transpeptidase, the beta-lactamase will break them open. Okay. So we combine these antibiotics with something else called beta-lactamase inhibitors, such as clavulanic acid, such that when we administer it, it can actually bind to these enzymes and occupy them, bind with them irreversibly forever, so they are not functional. Now, with antibiotic, can freely go here and do its job. Okay, Kevin. Second part of number 3. Mechanism of action. Why can't beta-lactams except inhibit beta-lactamase enzymes? Why can't beta-lactams except inhibit? Because they bind reversibly. Okay. Yeah. So I'm sorry. Yes. So the next part we'll talk about the importance of the strain on the ring. Okay. What? Good. Included in the final. Well, there should be something in the final. Well, if it's so clear, then why are you worried, Melody? Well, this is what I'm trying to do today, so I want to make sure I don't move next. I don't know. It depends. It depends how far we go. Okay, so we're gonna. Okay, Kendra. Like what? Okay, so we can. Good. Okay, right. So the previous material, we can talk about this on Sunday when we review, or today between 1 and 2. Okay, between 1 and 2 o'clock, we have a review today, right? So we can talk about anything in the past, and then basically try to make sure you understand concepts, not memorization, and basically everything we covered in class is the key thing to studying. If you see something in the notes that we did not talk about, then it's not going to be and if you're not sure, you can ask me. Okay, so but when you ask a question like, should this be like, should I study this or not, try to be more specific so I know, so I can answer you. Like sometimes you say like, do I need to know all the drugs? So it depends. If we're talking about like examples of many drugs, then no, but then you need to know the mechanism of actions. But some of the drugs, when we specifically talked about, like we really focused on, for example, Deltazim and Verapamil, because they have special mechanism of action. So then yes, you need to know these drugs. Okay. When we talk about the one for the HPs, then you need to know in generally how they act, not each one. Okay. Okay, I'm gonna move to exercise number 4. Okay. So, number 4 talks about the importance of the ring strain on potency, acid stability, broad spectrum, and the simplest way to think about it is the more strain the ring is, okay, then the more likely it will break in, for that acid, then the more likely it will attack the bacteria, so it's more potent, okay? And what else? What's the third factor? The more likely then the more it is, then the more it's unstable, or it will be more unstable. Yes. Exactly. So the more strained it is, then the more likely it will be susceptible to the acids, and the more potent it would be to the bacteria, right? And also, the more strained it is, then it will be actually unstable. Let's see. Potency, acid resistance, resistance to beta-lactamase, and allergy reactions. Also, what do you think? What's the relationship? What do you guess the relationship would be between the strain and the allergic reactions? More strained the ring is, more likely the allergic reaction will occur. So it makes sense. Like, it's like you have, a structure that is so unstable, and it's readily, to be broken in the acid. It's readily able to bind to the bacteria, cause allergic reactions, and since it's readily able to bind to bacteria, then it's also more potent. Okay. Now, among all these structures, which one is the most potent? Let me remind you of the structures of these 3 different classes. So roughly, we had something like that. Right? Am I missing something here? I think this is an S in here, isn't it? Cephalosporin. Yep. Actually, let's compare between the first ones because they make more sense. Forget about the monobactam for now. So, which one do you think is the most strained? Let's forget about the monobactam for now. Let's compare these alone, okay? Well, first of all, do you all agree with me that when you have a 6-member ring, it's less strained than when you have 5? So the least strained among all these is cephalosporin, okay? So this is least strained. Say it again. Why is it the least strained? Okay. If you remember in organic chemistry, what is the angle for an sp3 carbon? When you have a carbon attached to 4 different groups, what would be the angle? Do you remember the number 109? It was 109. So for the carbon to be comfortable and unstrained, it should be binding with all the other 4 atoms, and the angle between the bonds is 109. Okay? What's the angle here? It's a right angle, right? It's 90. What is the angle here? 90 and another 90. Okay? So you're forcing 2 angles here. Here you are forcing 2 angles. Here you are forcing one to be 90, the other one is like, let's say 120, or it's okay. So this is the least strained because you don't have as much pressure. I wish I have the modeling kit. I could actually have you build the molecule and see how tough it is to make the molecule. It's really difficult, okay? And there is no way you could actually make them flat. They have to come up like in an angle this way. But just imagine, instead of 109, you have 90 degrees. Here, you have 290 degrees, 290 degrees. So this is the least strained. It is still strained, but among all these, it is the least strained. Make sense, everyone? All right, so now let's compare between these two, penicillin and carbapenem. Which one is more strained? Why? Because of the double bond. So it's actually more strained than this because of the double bond. So if you want to rank them, carbapenem would be most, okay? This is least, and this is, let's say, middle. So now, since we know which one is more strained, which one is less, we can relate the strain to stability, okay? So which one would be more stable to the acid? Cephalosporin. Which one would be more potent? Which one will be like really, able to attack the bacteria much faster? Carbapenem. So it's more potent, okay? Which one will be able to cause more allergic reactions? Carbapenem, okay? Yet, if someone is allergic to one of them, there is a chance that this person will be allergic to the others, okay? There is a 10% cross-reactivity reaction, which means if you're allergic to penicillin, there's 10% chance you could be allergic to cephalosporin, okay? You have a question? What do you think? So the more strain, then it's ready to attack the bacteria much faster, and you only need a small amount of the drug because it can easily break and form the... Excellent. So the most strain is also susceptible to beta-lactamase, but guess what? The carbapenem, because it's also more strained, when it binds to beta-lactamase, it binds irreversibly. So it actually, yes. Yeah, so that's why it does not need to be combined with clavulanic acid, okay? Yes. The stomach acid. So having an acid will break open these rings. But when the rings are uncomfortable, when they are more stable, then they are less likely to be broken, okay? You got that, guys? Yes. Yes. So the same applies to the allergic reactions. Which one would be able to cause more allergic reactions? Again, the least comfortable or more strained. So we could say most strained also equal to least comfortable, right? Now, as far as the spectrum of activity, which one has more? And this is a tricky one because strain plays a role, but there's something else also that plays a role. So as far as spectrum of activity, what is the spectrum of activity for penicillin compared to cephalosporin? Penicillin is more on the gram-positive, cephalosporin on both positive and negative. Okay, but there is also other factors that has to do with the function group attached to these drugs. Okay, so and this was more like a trial and error. So you know they try different function groups and they get different spectrum of activity. So you know, don't worry about memorizing the broad spectrum of activity. I mean, the spectrum of activity for these antibiotics. You will have to do this later on when you learn infectious disease. It's going to be actually a lot of memorizations about where each antibiotic works on what kind of bacteria, and you know, you want to make sure you memorize this later on, okay? But for now, don't worry about the spectrum of activity, okay? Like the question I mentioned, whether the cefzolin in the rat, whether that cefzolin antibiotic works on the Staph aureus or not, you're not going to see something like that, okay? I just wanted to throw this in to have you think about the Helicobacter pylori in the stomach. So just to put the acidity as a factor. Yes, Melody? Broad spectrum of activity, rat, okay? So the last question in the rat, the one I canceled, this here, actually, I'm sorry, question number 4. You're not gonna see examples like that, you know, whether this antibiotic can be used for this bacteria or not, okay? So don't worry about the spectrum of activity. Yes, number 4 about erythromycin, I'm sorry. The erythromycin can be used in the Helicobacter pylori or not. So you're not gonna see, you know, like which bacteria does each one work on, okay? Yes.
You say again which one's going to be the most resistant to the beta-lactamase?
Which one is most resistant to beta-lactamase? So carbapenem is able to bind irreversibly. It's the only one that can bind irreversibly to beta-lactamase. So when it binds irreversibly, it occupies the enzyme and it basically prevents it, just like it will prevent transpeptidase. So then the antibiotic itself will be used by itself to bacteria. Huh? So the carbapenems, yes. Yes. Okay, so do you know, so does it make sense why one of them is more strained than the other? Okay, does it make sense how strain affects stability to the acid, allergic reactions, ability to attack the bacteria? Make sense? Okay, so you're good with this exercise too? Not yet? We'll ask questions then. Yes, ma'am. Exactly, that's one factor. Yes, ma'am. Yeah. You need to know the concept itself as far as which one is more stable to acid resistance or not. So for example, if you see 3 different drugs, one of them is a carbapenem, another is cephalosporin, another is penicillin, okay? Then you should be able to know which one is more stable to the acid, which one can cause more allergic reaction, and which one is more potent, okay? Okay, I thought that's what we just did. Okay, so let's do this. Strain is proportional to potency, okay, and proportional to acid stability, also proportional to allergic reactions. What else? Resistance, potency, allergic reactions. I think that's all. There's one more, which is the I'm sorry. The more strain is, so it's, yes, sorry. Yeah, inversely proportional to stability. So the more strain it is, the less stable to acids. More strain, it's more allergic reaction, more potent, and more resistant to beta lactamase. I'm sorry? Carbapenem is the most strained, and it is resistant to beta lactamase because it's by. So actually, cephalosporin is more susceptible to beta lactamase than the penicillin. Okay, so let's forget about the resistance to beta lactamase. Just know that carbapenems are exceptional because they form irreversible bond with the beta lactamase enzymes. Yes. So forget about the relationship between strain and the resistance to beta lactamase. Only know that carbapenem bind irreversibly to the beta lactamase, and that's why they are more resistant to beta lactamase. Okay. You still look confused. Okay, so as far as the relationship between strain and resistance to beta lactamase, disregard this part. Only remember that carbapenems form irreversible bonds with the beta lactamase, which makes them resistant to the beta lactamase. So if you fail with the penicillin, cephalosporin, you could use carbapenem, and they can actually protect themselves alone. we do not have to administer a beta-lactamase inhibitor like clavulanic acid, because they themselves can, attack the lactamase enzyme and bind to them irreversibly. Questions? Yes. Mhm. Yes, and some monobactams, right? Yes, not all, because I don't know much examples about them. So some monobactams also bind irreversibly. For the purpose of like today's lecture, just know that the fact that some monobactams and carbapenems bind irreversibly is an advantageous thing, because you don't have to administer beta-lactamase inhibitor. Okay. Yes, Zoya. What do you think? So when the antibiotic is so strained, it's uncomfortable, then it's easily able to be broken by the acid. It's also easily able to, be broken and bind to the target, the receptor. So you will need less of the drug. So it will be more potent. Okay. So potent. So the more strain, then you need only less amount of the drug, and the more strain means that the drug can easily break under acidic condition. Also, the more strain means they can attack the body proteins and cause allergic reactions. Okay. Yes. Okay, question is, do we need to know the difference between first and second generation? No, I mean, only as a pharmacist, you should know that, as we advance to second, third, and fourth generation, these newer generations have a broader spectrum of activity, okay? And they normally are more available as orally and IV, so it's more enhanced features, okay? But I do not expect you to differentiate between first and second. You will have to do this. You will have to know this later on when you learn from, clinicians and from the clinical department. You will need to know the examples from which ones are first, which one is second. And, the trick is always look in the common name, see in which name, you'll find something common in the name that can tell you whether it's a first or second or third generation. And there will always be exceptions, but then once you know the common feature in the name, then, and with the exceptions, it will be easier for you to know which generation it belongs to, okay? So, I mean, this is not for my part, for later on. Brand and generic, I never expect you to know the brand, the generic. I always provide both of them to you, but you should learn at least the top 200 commonly used brand generics, because these things you need to know for Naplex and for other topics, clinical topics, you will be expected to know the brand and generic, okay? Right. Some people were raising their hands. Yes, ma'am. In terms of potency, yes. So when you have a drug that's more strained, then it's more potent. But I mean, they all have the same mechanism. It's just, when it's more strained, then you only need less amount of the drug. Now, as far as stability to the acid, strain is one factor. Another factor is, which group is attached to that R ring that hopefully we'll talk about next, okay? So there's more than one factor that affects, the acid stability, okay? Yes, Moody.
So if there's more strain, that means it's easier to break down an acid. So that means you should administer it by IV or IM.
Generally, that's the goal, yes. But these problems have been resolved by adding other groups to make the drug more stable. Like for example, penicillins, they're in the middle, they're not as much strain, but you will see penicillins given IV and orally. Cephalosporins, although they are most stable to the acid, but you will see drugs given IV and orally. Some drugs are not stable to the acid, okay? So one factor is the strain, but another factor is, this group here, whatever is attached here. Let's call it the R group, okay? So somewhere here, there's an R group that also plays a role in the stability to the acid. In the case of the cephalosporins, there's also another group here. Let's call it R2, also plays a role, okay? But, we'll move one step, step by step to make sure everything is clear. You guys look so depressed. What? President, what's going on? Do you want to make this whole lecture just optional reading? I'm serious. But then you promised me for the rest of the lecture to ask, good questions. Okay? So let's move on. All right, so let's move on. But then, think like someone who wants to learn, not someone who's worried about the exam, okay? So it's a different mentality, right? So now you sit and relax and think, oh, so what do I need to know as a pharmacist? But then, yes, Kevin? Say it again.
Yeah. Yeah.
I know. Oh, no, I know, you're right, of course. Yeah. So, but I mean, I'm trying to find a way where you could, be fair, right? I mean, we want you to learn, but then at the same time, we cannot just, have you all, you know what I'm saying? I mean, you have to, like, I guess, do your part, right? Yes. Sure. I'm sorry, repeat this again.
Pick a different day. You're saying you're concerned that we won't be asking questions. Pick a day that we've already asked a lot of questions, but maybe it's still not clear. There's a lot of struggles. Maybe it was just a lot of material, and make that one an optional day that we've already gone over and asked questions. And then this one will be fresh in our mind for the exam, because that way we already learned it, but then we don't have to spend as much time because there's just so much information.
You mean continue what we have today and then keep it in the exam, and then you guys pick a different topic and then...
Get rid of the one that was more information on a different day.
Okay, well, let's do this. Let's continue like normal lectures, and then you work together as a team. You have a president, and then you decide to remove one most difficult topic. Make sense? Okay? So it could be today's topic. It could be one of the previous topics. Just let me know which ones you think was not clear. So let's continue today and see how it goes. And then if you get everything today, this might be your favorite topic, right? Well, you never know. Yes, Kendra. Yeah.
But this is a small portion compared to everything.
I know, yeah. But you're only responsible for what we talk about today's lecture. That's the thing. So if there is things in the notes we did not visit, then I cannot expect you to.
So basically, we'll take one day off of our Tuesday and the election day, and we can vote on it the
Okay, so let's continue today, and then you guys communicate with each other. Let me know which one, but you need to do this soon because I need to know, which topic is most unclear to you, so I could take it off. Okay, fair? All right. All right. So the next one, let's see, exercise number 5. We already talked about that in exercise number 5, the significance of the periplasmic space, right, guys? So why is the periplasmic space important in the gram-negative? Because it traps beta-lactamases, okay? Okay, number 6, rationale behind designing acid resistance. Okay. Okay. This thing here is called periplasmic space. Okay. Here we do not have this space. So why is this important in the gram-negative, but in the positive we don't? I guess what is the impact of having this space on the resistance of the bacteria? The beta-lactamase enzyme will be trapped here, so it will be more concentrated here, so it can protect the bacteria from the antibiotics. Here, even if the gram-positive bacteria makes the beta-lactamase, it will diffuse through the cell wall. The only mutations of gram-positive bacteria that are resistant are the ones that are able to produce the beta-lactamase in large concentrations, quantity and speed. So they're producing beta-lactamase so fast so that even when they diffuse out, there's still someone here that protects the bacteria. Make sense? Gram-negative, they can easily produce some beta-lactamase. They will be trapped in here and they become resistant. Okay. I thought we already talked about that. So clear now? Move to the next one. Okay. And then number 6 talks about the acid resistance. Number 7 talks about the resistance to the beta-lactamase. And then number 8 talks about broad spectrum. Number 9 talks about combining all these together. So the best way to look at them is look at the notes here. Okay, so we have 4 problems, okay? The first one is acid resistance. The second one is being susceptible to the beta-lactamase enzymes. The third one is the broad spectrum, okay? I think these are only 3. The fourth one is actually, the fourth example is combining all them together, right? Right, so number 4 here talks about, number 3 is combining the acid and ligands. Okay, so I'm sorry, three problems, right? Broad spectrum because penicillins, and here we're talking about penicillins, okay? Penicillins, they are mostly affect gram-positive, some gram-negative. So we want them to be more effective. We want them to be able to inhibit gram-negative as well. So broad spectrum is an issue. Second, they are susceptible to the acid. So the first penicillins, penicillin V, actually penicillin G, I'm sorry, penicillin G was susceptible to the acid. It could not be given orally, okay? And then the third problem is the fact that it could be broken by beta-lactamase. So as far as acid stability, I'm not worried about the, how the attacks, how the electrons shift and move in the presence of the acid to break open the beta-lactam. But I just want you to know that adding an electron withdrawing group, okay, and you don't have to know all the electron withdrawing groups. I'll be giving you examples. So I'll let you know that this group is an electron withdrawing group, okay? So adding an electron withdrawing group right here helps making this ring more stable, okay? So that's problem and a solution. Problem, instability to acid, and then adding electron withdrawing group makes it more stable. And then as far as resistance to the beta-lactamase, we already saw in the rat exam that having the O-methyl group here, or ethyl, will make it resistant to beta-lactamase. And we also mentioned that the size of this group is important. If you increase the size more than an ethyl, then it becomes not only resistant to beta-lactamase, but also to the transpeptidase enzyme itself. So the best size for the group is methyl or an ethyl, okay? More than that, the drug cannot bind to its target, which is transpeptidase. Less than that, the drug will be susceptible to the beta-lactamase, okay? Now, can we combine the acid stability and the beta-lactamase stability? Yes, we can. This is a group here that is both bulky and electron withdrawing group. Make sense? So now you could protect from beta-lactamase, and you could actually make it stable to the acid, okay? The last factor is tricky. When we talk about broad spectrum of activity, then it's a trial and error. So different groups were tried to see how we could make the drug act more in the gram negative than the gram, than just the gram positive. Okay, so think about that. Let's have a break, okay, and come back and we'll continue. Right, so 10 minutes break and come back.
Said adding an electron withdrawing group helps make it more stable, but the size is important, either adding a methyl or an ethyl to the O. Okay. Okay, guys. So this is everything that we've gone over. Sorry. Thanks, Dr. Khashan. Oh, okay. So this is everything that we've gone over from Cat 2. So what I need for you to do is by 12 o'clock, email me which date you want taken off. Or that's what you said, right? You said one day you would take, okay. So whatever you want, that's fine. You want to just do it now? Oh, okay. All right. Okay. So do you mind if we do this real quick? Okay. All right. So take 2 minutes. Hang on. Take 2 minutes to decide. Let's say, can we say 5? Would that be okay? Take 5 minutes now to decide which date you want. Discussion. Melody. Sure.
So if we, the stuff for today, you're gonna very clearly delineate today, right now in class, while we have time, what would be from today on the exam.
Or just.
So, but then,
Are you meaning application wise? That's what would be on the test since we've, is that what you mean?
right. So so today I'll cover the important concepts. Some of the things that are in the notes or in the material, if we do not talk about today, it's not included. Now, I'll make sure you understand everything, but it's up to you. If today is not really your favorite topic, then it's up to you guys whichever your topic you wanna take off the final. Okay.
So what other questions do you have for Dr. Khashan right now, Melody?
So then I would take instead of doing my own, see how far we get.
That's a good point.
And then vote. Because if we don't even get very far today, and there's another day that's so much, we can eliminate so much.
Okay,
Yes.
I'm getting a lot of other discussion, guys. What raise your hand. Let me know, let us know now what you think. That's what I'm saying. That's okay, so that's what table 12 thinks. Table 12 says to wait. Okay, you're yes, ma'am. Okay, October 2nd. What about it? Right, part 2 is optional. Okay, well, I didn't write it, but part 2 will just, we know that that's optional. Thank you, Dr. Sean. Yes, ma'am. T. Okay, thanks.
Okay, so let's continue. And you guys can communicate with Kendra, and she will let me know. Okay. Okay, so I really think the acid, the 3 factors we talked about, as far as broad spectrum, it's hard to know until we check, these function groups and know which ones have broader spectrum or not. It just happened that these groups, the NH2, OH, CO2H, were actually found to cause the penicillins to have broad spectrum of activity. Okay, so this is not something we could really rationalize why is this happening. Now, the only I guess rational approach as far as this part is how to make the drug acid resistant and beta-lactamase resistant, which is very simple. You look at the structure and you will see part of this. You look at this part of the penicillin, okay, this group here, and then ask yourself whether it's bulky, whether it's electron withdrawing group, or whether it's both bulky and electron withdrawing group, or maybe none of the above. Okay, so if it is electron withdrawing group, what does that mean? It's acid resistant, right? Which means it can be taken orally, right? Okay. If it is bulky, it means it's beta-lactamase resistant, right? If it's both bulky and electron withdrawing group, what does that mean? Make sense? That's it, that's all. Okay, now you do not have to know which functional group is electron withdrawing. This is something that will be given to you, okay? So I will point to the functional group and say, this is an electron withdrawing group, okay? This is a bulky group, okay? You just have to look at the structure and see whether it has these two features, one of them, none of them, okay? Okay, Melody.
You said add electron withdrawing group and a smallish bulky group.
Okay, now as far as bulkiness, we have optimum size for the bulky group, which is methyl or an ethyl. If you go more than that, if you go larger than that, then guess what? You are not only blocking the beta-lactamase, but you are also blocking the transpeptidase, which is our target, okay? So we should find the optimal size, okay, to block only beta-lactamase, but not the transpeptidase. Okay, guys? Yes, ma'am. What do you think? If it's both bulky and electron withdrawing, what do you think is? That's it, you got it. She was asking if, what happens if the group is both bulky and acid resistance, and then she answered her question by saying it will be both acid resistant and beta-lactamase resistant. So electron withdrawing group and bulky means it's both, okay? Here is an example here. It says bulky and electron withdrawing. So guess what? This drug will be resistant to the acid and will be resistant to the lactamase enzyme. Got it? Clear, guys? Okay, I'm gonna move to the next exercise unless you have another question. Any questions? I'm going to actually skip exercise number 10, okay? Because conceptually, we talked about the same idea with the penicillin. If you're curious, position number 3 at the cephalosporin can also affect, the stability of the drug. It affects the pharmacokinetic property, how it's orally available or not, and so forth. So we'll, you could have this for for your own education, for fun, okay? You could look at this part. Yes, ma'am. Right, so 6, 7, 8, and 9 talks about acid resistance, beta-lactamase, susceptibility, and the spectrum of activity. And we already said in the case of spectrum activity, we really don't know, what's the rationale. We simply try different function groups, and then we found some of them to enhance the, the broad spectrum of activity, and others don't. Okay. Okay, skip number 10. And then 11, explain the role, C alpha. Okay, forget that too. Cephalosporin mixed acid. This is the same. Okay, 13, I think we already answered that. What makes carbapenem the best beta-lactams? Because they bind to the beta-lactamase enzyme irreversibly, right? So they protect their own, they're resistant by themselves. So it's like, they don't need clavulanic acid to help them, like the case of the amoxicillin. Okay, compare between beta-lactamase inhibitors and beta-lactam antibiotics. What do you know that? So we have beta-lactam antibiotics, but then we have beta-lactamase inhibitors, which are clavulanic acid and sulbactam. Was that one of them? Yeah. So inhibitors, we have sulbactam, tazobactam, and clavulanic acid, and avibactam. All these are specialized to only bind to the beta-lactamase enzyme. Okay? Yes, ma'am. Not for my class. You will need to know this later on, but for my class, I'll provide both generic and brand name. Okay.
But we do need to know all those names that are inhibitors. We need to recognize those.
So actually, I would want you to know that clavulanic acid because it's really very common, and you should know that if you see it, you know, you've seen that in the pharmacy. Augmentin is always amoxicillin clavulanic acid, so you should know clavulanic acid. The others, you can tell only from the frame bactam. So you have sulbactam, tazobactam, avibactam. So anytime you see bactam, then it's actually beta-lactamase inhibitor. Okay, so I'm giving you a tip to memorize it. Okay. And the examples of the combination of these two, I will provide this for you. If like you know, I would say, for example, unison, which is a combination of ampicillin and sulbactam. Okay, and then I will tell you that zosine, which is combination of this and that, and so forth. Yes. Okay. Good. So do these antibiotics work? I mean, sorry, beta-lactamase inhibitors. Do they work as potentiators? I mean, do they act as potentiation or addition of synergism? You remember these three different ways when you combine two drugs together? We all agree that they enhance the activity of the other antibiotic through potentiation because they themselves have no activity. Okay. It's not addition, it is not synergism. Okay. Okay, protein synthesis process. This was just a review. You already have taken biochemistry, you know the protein synthesis process, okay? And then this is also a general mechanism of protein synthesis. So now we have finished beta-lactams. We're talking about another mechanism of action for drugs that prevent protein synthesis. Now let me ask you this. Drugs that kill bacteria, or I'm sorry, antibiotics that works through protein synthesis inhibitor, are they bactericidal or bacteriostatic? You know the difference between static and cidal, right? We all know that beta-lactams are bactericidal. What about the protein synthesis inhibitor? Are they bactericidal or static? Static, right? They do not kill the bacteria, but they stop the progression of the bacteria. They stop protein synthesis, they stop the development and the growth of the bacteria, okay? Because they inhibit the protein synthesis, right? The protein synthesis inhibitors, okay? Okay, exercise 17 and 18 talks about tetracycline and macrolides. I think the most important features of tetracycline, I really want you to know as a pharmacist, is first, chelation. So you should not combine these with dairy products, antacids, okay? Also, the fact that they increase sensitivity to the sunlight. Okay, guys? It's really important when you counsel sensitivity to sunlight, yes. Sunlight, yeah. So it's really important to counsel people on tetracyclines on both these two things, okay? So if someone takes tetracycline, what should we advise them to do? And first, separate from any dairy products, milk, antacids, multivitamins. What else? Sun, be careful. What do you do that? Stay home all the day? What if they want to go to the beach? Use sunblock, right? Yep, sunblock. Okay. So, but then why tetracycline cannot be given to children or pregnant women? Developing bones. What's up with that? Bones needs calcium. Tetracycline binds chelate to the calcium just like they chelate with the divalent and trivalent. So they bind these calcium and then they become part of the teeth or the bone of the the children or in the case of pregnant women in the bone. So you will have a yellow discoloration, permanent yellow discoloration in the teeth if someone takes tetracycline, like kids if they take tetracycline, because the tetracycline will stay with the calcium, it will stay in the teeth forever. Okay? So these are the three major things: photosensitivity, chelation with vitamins and minerals, and what's the third one? No children or pregnant women. Okay? So that's the other thing I want you to know about tetracyclines. Any questions about this so far? And of course, the fact that these protein synthesis inhibitors are bacteriostatic, not cidal. Should we talk about macrolides? Somebody says no. Yes, ma'am. Because the baby is still developing their bone, so then tetracycline can bind to the calcium and be part of the bone. And my guess is somehow it affects the bone development. I'm not sure how. Okay. Macrolides, yes, question? Okay, so the idea is the protein synthesis inhibitors, they only freeze the bacteria, but they do not kill it. Okay, so they prevent the synthesis of proteins, and the bacteria cannot, grow further, and so they rely on the immune system to get rid of these bacteria. They only freeze them. Okay. Yes, Melody. Okay, that's a good question. So do I need to know which class of drugs are are protein synthesis inhibitors? I mean, normally if I covered all the antibiotics, then yes, that might be difficult, but we're only covering two classes so far. So we had beta-lactams, which is, penicillin, cephalosporin, carbapenems, morobactam, okay? And we have protein synthesis inhibitors, which are tetracyclines and macrolides, which is clarithromycin, erythromycin, and all that. So honestly, I really want you to know that these the examples of tetracyclines or clarithromycins that are protein synthesis inhibitors. So you should know their mechanism of action just by the name, which is very simple. Tetracyclines will always end with the cycline, doxycycline, tetracycline, and minocycline, right? And then you have The macrolides always ends with like erythromycin, clarithromycin, azithromycin. Yes, for this part, because later on you will see other mycins, but they have a different mechanism of action. So, but because these are the only examples we're covering, that should work for you. Okay. Okay, macrolides. So these are the only thing we need to know about tetracycline. Macrolides, actually 18, we could link it with 19, because the only thing I really want you to know in the macrolides is how the erythromycin acid instability and bad taste or bitter taste was solved. Okay, so as far as acid stability, how did we fix the problem of erythromycin and avoid being destroyed by the stomach? Number one, enteric-coated delayed release, right? So erythromycin is formulated in a delayed release form such that it can actually pass the stomach, go to the intestine, get absorbed there. Okay? So as far as acid stability. Number two, we modified the structure of erythromycin. We added some function group to protect the part that's affected by the acid. Okay, we added, I think, chlorine, which made it clarithromycin. Was it chlorine? Can you hear me now? All right. Yes. Oh, you have batteries? AA. Remember the ad about, can you hear me now? Can you hear me now? You do? AA? Yes. Okay, so we talked about the acid resistance. One way is to use enteric coat such that it passes the stomach, goes to the intestine, get released there. This is in the case of the erythromycin. Now with the clarithromycin, okay, we modified the erythromycin, we added methoxy group and stabilized the drug. Now it's stable to the stomach acid. So that's why clarithromycin can be taken orally, I mean, without the enteric release. They could be taken and they can pass the stomach, will be stable. Okay. A third example is azithromycin, which is the Z-Pack or Z-Max or Zithromax. Okay, this drug, the ring itself has been expanded. Okay, because if you look at the structure where the acid is causing the reaction, it's because two groups are next to each other. So when we extended the ring from 14 atoms to 15, then these two groups are now away from each other. So then the drug is no longer able to, be broken in the acidic condition. Okay, so that's the third. This is an example how the azithromycin. This is the example why azithromycin can be taken without the enteric coat. They can be stable to the acid. You got that, everyone? Okay, so enteric coat, or adding methoxy group to get the clarithromycin, or expanding the ring and have the azithromycin, which is Z-Pack. Okay, so why do we take Z-Pack to the first day, then 111? Loading dose. Good job. Thank you. You still remember the loading dose? Good. Okay. Now, what about the unpleasant taste of the erythromycin? How did we fix that? One way is a prodrug. So the prodrug is insoluble, such that when you take the drug, it does not dissolve on the tongue. That's one way. Or you could make the prodrug in a way to mask the function group that's responsible for this horrible taste. So now this drug tastes differently or have a different taste, okay? A third way, which is very simple, is what? Sugar coat, right? You could sugar coat the tablet, and then when you take it orally, it does not touch your, taste buds, and then that's it. A fourth way is the enteric coat itself will also not only protect the drug from the acid, but also prevent it from dissolving in the mouth. So then you could actually, avoid the horrible taste. Clear? Did I miss anything? Film coat, electric, or film coat are these sugar coated. Enteric coat we talked about. Make it very insoluble, like the case of the stearate. Okay, erythromycin stearate. And we also have a prodrug, which is ethyl succinate, such that the drug has a different taste. Notice that in the case of the stearate, we have a prodrug that's insoluble. Okay, it's an ester, right? And then we could also have ester groups to make the drug more soluble. So remember, esterifying a drug can make it more soluble or less? Both, it depends. I mean, not both at the same time, but esterifying a group could be used to make the drug more soluble or less soluble, okay? It could also be used to, in the case of prodrug design, to improve the taste, enhance absorption, all these solutions we have seen. Okay, so anything we have not talked about in today's lecture will be for your own information. Okay, I have 10 minutes left. I can answer questions or go through only the important things about, just for your own education. The third part, like the sulfa drugs and folic acid inhibitors. Answer questions better. Okay, because the only things I really want you to know from the third lecture, which is the topoisomerase inhibitor, is that the fluoroquinolones like Cipro and ciprofloxacin and levofloxacin, these drugs, they share the same 3 features of tetracycline. First, they should not be combined with minerals, okay? Second, they cause photosensitivity. And third, they should not be given to pregnant women because they can cause teratogenicity. They can affect the development of the fetus, okay? So these 3 features are common between tetracyclines and quinolones, such as Cipro. So this is just so you know, for your information as a pharmacist. And then we have the sulfonamide. We already talked about the sulfonamide allergies, right? The antibiotic sulfonamide and non-antibiotic sulfonamide. So, the allergies we covered already, like if somebody is allergic to sulfonamide, does not mean that they could be allergic to the other non-antibiotic sulfonamide, such as what? Morphine sulfate, the glipizide, and all these diuretics, thiazide-like and loop diuretics, okay? The only thing I want you to know about the antivirals are the fact that they are combined to avoid resistance. Normally, when we treat someone with antiviral, then a combination of drugs is used. So I do think if there's other things. Anyways, so questions? Yes. Say it again. Oh, sure. Do you wanna? Well, it's up to you. Do you wanna? I'm trying to use the time as much as you. Right. So let me see if you have any questions about today's lecture, and then you can do the. Yes, ma'am. Yeah, so there is not really much about monobactam. So if you, yeah, yes, cephalosporin, penicillin, and carbapenem. And if you have noticed, the cephalosporins, actually there's a lot about cephalosporins. We skipped a lot of information because the same concept applies when it comes to penicillin, modifying the group to make it more acid stable or so, cephalosporins, I just want you to know the relative potency and acid resistance because of their strain or because of the ring strain. Okay, so basically what we talked about today. Okay, so if you look at the exercises, I basically canceled 10, 11, 12 because they talk about the cephalosporins. Okay. Okay. Any questions about today's lecture? If you're not sure about something, like if you're really not sure I should know this or not, please email me and I will share my answer with everyone, okay? Well, let me ask you if you wanna just, end now, or do you have questions? Do you just wanna stop now and go with the vote? Raise your hand if you have no questions, raise your hand. No questions? Okay, so it's all yours, Kendra. Do you want me to stay or leave? It's like, okay, so let me wait and see the outcome.
Is there a marker? Marker. Okay, guys, we're gonna make this quick because we've got open lab in 5 minutes. So basically, we'll just go group by group. You give us a day. Are all of them on there? Hang on. Y'all need to agree. Well, no, that's 93 people. That's not gonna happen. That's a lot. It's a lot of people. I'm sorry. So yeah, decide now amongst yourselves. Or groups, sorry, amongst your groups. Yeah, we're just writing the dates down. Give us just a second. Yeah, well, you know how to work this thing? How do you make it smaller?
Zoom.
Basically, he said there were a couple things you needed to know from folic acid. Other, but yeah, antivirus. Okay, we're gonna go ahead and get started. How about we start with table 1? Are you guys ready? Okay, which date would you like to have removed from the test? Today's, okay. Group 2, 9/27. Thank you. Group 3, 10/2. Thank you. Group 4. I'm sorry, Group 4. 9/29. Thank you. Okay, Group 5, 29. Okay, Group 6. Today's Group 6 says today. Okay, Group 7. Yeah. Okay. Group 8. Group 8. 22. Okay. Group 9. Group 10. 5, 6, 7, 8, 9, 10. That's half, isn't it? Group 11. Group 12. I think that wins it. Yeah, okay. That's 12. 13, 1's 29. 14, 1's 20, 29. 16. Okay. 29 it is. Thank you guys very much. For those of you that don't know, we do have open lab now. It's upstairs, not in our classroom. It's in a small conference room across from Dr. Brazil's office. So that's from 12 until 1, and then come back here at 1 for Dr. Khashan's review. Thanks.